So today I'm going to talk about Noly, and Noly is a library that has been recently open sourced from Nubank. And the idea of the library is to be a way of declaring data dependencies, build dependence, declarative dependency graphs with conditionals. And I'm going to explain what that actually means. So before we go into what do I mean when I say conditional dependency? First, I want to go back and talk a little about direct cyclic graphs. So let's say you have a function, a simple function in Clojure, z that depends on x and y, and it just sums x and y. So very simple, easy to understand. So we can analyze the data dependencies from this function with a simple DAG, a direct acyclic graph, uh, which are just direct arrows that point to where the what depends on what. So in this simple DAG, on the left, z node depends on y and x, and that's indicated by the arrows. So now on the middle side, we have a similar function that also depends on x and y. But inside, in the body of the function, we have a conditional state, right? So if x value is even, then we are going to multiply x by itself. And if x is not even, then we're going to sum x and y. So now we have something different that uh, is is not the same as what we had before. Even though the function is saying that you're depending on x and y, that's not entirely true, is it? Because it's true that you always depend on x, but depending on the value of x, you might depend on y, you might need y or not. So if x is even, then you don't depend on y, you just need x. If x is odd, then you need x. So how do we express this with a DAG? It's not straightforward to do it, and that is not a proper way of expressing this kind of conditional dependency. So instead we have to go with another thing, and I don't know what this thing is and what it should be called, but it's something that might look a bit more like the thing on the right. So you have a conditional, and the conditional depends on x, right? You need x to calculate the conditional. And depending on whether x is even or odd, we have two different DAGs that may arise from this. And it's not clear which of the DAGs are you going to use until you actually calculate the condition. Until you get x, then you check the x is even, and then you know uh, what shape in terms of dependencies the node W is going to become. So this is what we mean by conditionals, by conditional dependency, by expressing conditional dependencies. So what Noly deals with is not just DAGs. Of course, you can write DAGs with Noly, but you can also write conditionals, and this is sort of like a superset of DAGs. And I haven't find a lot about this kind of structure in the literature, but if anyone knows, please tell me, because I would be interested to read more. But in any case, so how is Noly structured? The library itself is composed of three parts. The main part is the data structure definition that is just a map is just like a definition of how uh, we're gonna define the nodes. We have like a branch node, a leaf node, sequence node, and I'm gonna explain those later. But uh, all those kinds of nodes and what are their structure are defined in this definition. And we have syntax sugar that's human readable. That's for humans to write. So this is on the bottom right here. You can see how we can write the same uh, thing that we saw on the previous slide, same branch. So it is a constructor, syntactic constructor that receives three other nodes. And first one is the conditional node, the middle one is the truthy node, and the third one is the falsy node. So the conditional node is the condition itself, and if the condition is truthy, uh, we apply the truthy node. If the condition is falsy, we apply the falsy node. And when you write this, what it actually does is just translate this syntactic sugar into the thing on the top right, which is the data structure definition. They represent the same thing, but this is machine readable. I wouldn't want for humans to type down this by themselves. Instead, that's why we have some syntactic sugar to make it easier. But the information on top right is the same, right? So you have a map that represents a branch, and the branch has a condition node, a truthy node, a falsy node, and each of those have their own information as well. You can see here on the inputs are the keywords that they depend on. So I can see the condition node depends on X, the truthy node depends on X as well, but the falsy node depends on X and Y. So this way we can express in a richer way what uh, what a conditional dependency means and what are the actual dependencies in a branch. Finally, with this data structure, you can execute them several ways, and we support several engines. The simpler one is the synchronous one that will execute everything synchronously, and we support core-async. We have some other experimental engines that use promesa and manifold, and many more are possible. So you separate how you define things. We separate the syntactic sugar, how the humans write it, how the data structure is in the end, and the engine depends only on the data structure definition, and you can write as many ways of interpreting this as you want. So the best way to show what this all means is through code. So let's jump to the REPL. And I have this is the samples. This is the samples tutorial. It is on the README on the repository. If you want to go to the Noly repository, you will find the tutorial there. I think it's the first link on the README, and it's the same thing, and you can follow up or look at here if you want. So the first definition that we're gonna go here is a value node. A value node is declared by just this a greater than value, and if you what this actually is, you can see that it's just a map that has type value and the value inside it. And this should define like raw values, things that you don't need to evaluate. You just take it as it is. The other kind of node is the leaf node. And this is the node to express strong dependencies. So in this node, we have the sum of A and B, and we use question marks to express the dependencies, the missing values. And in this case, this is going to be a key equivalent to a function that depends on A and B, and when they receive A and B, they sum the values. So if you can see what declaratively actually represents is a map. I believe it has the inputs in it, which are A and B keywords, and a function. So the function here is a function that's gonna receive the map with the values, and you can easily evaluate this node if you want to troubleshoot and see that it does work as intended. You can use eval node with values and pass in inside the map the values that the node needs, and it will evaluate. In this case, it evaluates to 3, so it sums A and B, and you get 3. So far, nothing really impressive, because it's what a function does, right? And but finally, we have also a way to express branches, and this, I think, it gets a little more interesting. So in this case, we are expressing an node which is a branch, and the first node of the branch is the condition that A is even. And if A is even, we have the node that represents the value that we wrote before, and the other node, which is the A that we declared above, that depends on A and B. So you can use them directly here. You could paste them directly here, but it would be the same as just saying just using the node which is there already. So if we take a look at a branch, what we have is a data structure with a condition, which is a leaf node that depends on a truthy node that has a value, and a falsy node that has a leaf node that depends on A and B. And you can use the same eval node values, and that to get a tree. So because in this case here we are passing 1 for A, which is odd. So A is odd, then it goes to evaluating A leaf, which sums A and B, which is 3. But if in this case A is even, it's going to evaluate to 1, which is the value which we put on the truthy node. So same thing that we would expect for normal condition. And in this if syntactic sugar, we can also place values directly. So instead of having a value node, we can just pass in the value, and the function will figure out it is a value. So if you look at a branch node, a branch 2, you can see that the truthy node, we we replace the one here for a value node that has one in it. So there are other ways to express branches, and those are just syntactic sugar because in the end all boils down to branches, right? Branches are the, the main data structure for dealing with conditionals, and uh, so this is uh, the same if statement that we expressed before, but expressing with cons. And this greater than con should be similar to how cont already works in Clojure. So we have a left-hand side and right-hand side. We have several clauses, right? And the final clause, which is here saying the else clause that will catch everything because else is going to be equivalent to truthy. So if you go take a look at what another branch becomes, it's just going to become a branch like data structure. Just the one caveat is that the faulty node is actually a branch node because in the similar way that con works closure, that when no condition matches, it returns nil. And this con also works the same way. So the false node is actually a condition that on the truthy side will be this leaf. Here the sums A and B, and the false side will be the value node of new. And we have other syntactic sugars for other conditional expressions, and I'm not gonna run through all of them because they should be the same as you expect from closure or closure and. So you have this greater than or expressing or like conditions, and greater than and for expressing and like conditions, and they should behave uh, the same way. Finally, we also have the sequence node. This one is I don't think it's hard to understand what it does. It's similar to what a map is in Clojure. So for a sequence node, you pass a function that will take a value and do something with it, and you pass your question mark symbol to represent the thing that you're gonna need the sequence to evaluate, which needs to be a sequence. So if you evaluate this and you pass a map with A being the sequence 1 to 3, what sequence does is it's going to apply the function that we defined, which is inc, and it's going to return same sequence, but each value incremented by 1. So the next thing is in terms of concepts that Noly has are environments, for lack of a better name, this is how I'll call it. And an environment is just a map of keys and nodes. So on the left we have keywords, on the right we have nodes, and it's just a way for naming uh, the nodes that we have inside the context. And we have a series of helpers to use those amps as well. So here you have a simple amp that on A keyword we have a value of 1, on B we have a value of 2, on C we have uh, a function that sums depends on A and B and sums in A and B. So let's say we want to evaluate C, in the context of this app, and using eval key just does that, and it's going to return 3, just the result summing A and B. You can also use eval node. This is when you want to supply a node that is external from the M. So here I'm finding another node, and it's this node is multiplied 3 and B. So in the end, B is 2. So if we multiply by 3, you should get 6. And what you get, uh, this is a way that you can supply something from outside the environment itself. Another helper that we have is eval, which is the most basic one. So let's say we have the env and we want to eval C, and what eval returns is the whole env again. C, if we gonna the ref. So eval is going to return another env, but now uh, instead of the leaf C, we get C as a value because it was already evaluated. It evaluates to 3. So when we get this env, we got all the values now. Another helper is just get value, just like anything fancy. So you have an env here, and then I want to the value of C, assuming that C was already evaluated, and just returns the value unwrapped from the value node. Now we are also able to run with different engines, as I said before. So that is by supplying optional keyword here, and one of those engines is the sync.lazy one, which is the simplest one, which runs everything synchronously. And you can also supply any one of the engines that we have available, and who is going to use that for evaluating. Now, one of the interesting parts, but is when we have an env and the env has conditionals in it, right? Because, for instance, this environment here on the Y, we are simulating an expensive computation. So this computation on Y takes 10 seconds to run. There's a thread lead to simulate. It takes a long time. This could be an external HTTP request. This could be an expensive query or expensive computation. And the trick is that we don't want to run Y unless we have to, right? Because Y is expensive, and if we don't need Y, we don't want to run. And usually all the engines that Noly implements right now, they have this behavior. So they only calculate things that are necessary, and they don't eagerly calculate things that they're not needed for what you want to do. So in this example range here, if we evaluate Z, we see that X is something that evaluates to true, and true is even, right? So if true is even, then we're just going to return X itself. So we don't need Y. So this should run immediately. It should not. It does. should not return. It should not take 10 seconds to run, right? And so finally, we have some helpers to help with async programming. This is specially tailored for core-async, for instance. And this is used to prevent blocking threads. So let's say you have an HTTP request that returns an async channel from core-async, and you want to uh, use that, make sure nobody understands that, and you want to make sure that this HTTP call that you're making, it's not gonna block a thread. It's gonna be not blocking IO. So the way we currently do this, provided you are running this with the core async engine, then you get this non-blocking capability. You use a channel leaf. This is a special kind of leaf that is going to inform the engine that what what follows here is going to return a channel. So this code here returns a core async channel that sums A and B, right? It depends on A and B. And we can also use the same helpers that we were using before. If you want to pass this out, you can just pass in placeholders for the values and it should work the same. We should evaluate the same because uh, this is also going to be compatible with all the other engines by the way we defined it. It's just that uh, it's just that if you want to take advantage of this, you need to for us to have non-blocking IO. For the moment, you need to run it with the core async engine. Then you're gonna get non-blocking IO. If you run this with any other engine, it still works. It still get the right value. It still evaluates, but you just run the risk of running some IO and blocking a thread while doing it. So that's the only caveat. So finally, here we have an app which uses the node, the async node that we defined here. And we can use another helper, which is a bulky channel. And a bulky channel it evaluates things, but it returns an async channel instead. So that you can choose when you want to take the value from the channel. So you should, if I run this on the REPL here, about each channel, it returns an async channel. And if I want to have the value out of it, I have to do a blocking take here from core async. And if I do it with the blocking take, I should get the result out. So this is just so that you can have control of when you want to block. Those are the all the helpers that Node has. It is defined. Everything is defined here in Node API v0, and I think that's the basic for the tutorial. And moving on, I get to tell you the story about how we can use this for decoupling logic from side effects. And this is one way we can visualize this. So on the left side, we have a code that's very a common pattern in service code. You make a request to some service to fetch data, right? And depending on what value, what result you get from this, you're gonna do something. Otherwise, you're gonna do something else. So if um, depending and on the value of A, we do something, and depending if A is falsy in this case, we're gonna make another request, uh, a request to B, and then we're gonna do something with B. And in this left-hand side code, we have side effects making HTTP requests mixed with the green part of the code, which is pure logic, and it's all intermixed, and we have a branch in between, right? So if you do this with Noly instead, you're gonna get the thing on the right hand side. So we're gonna use a channel leaf here because we want to make an async uh, HTTP request, and so A is one request, B is the other request, and it's missing one parenthesis, but try to ignore that. Anyway, so the response is just the logic that you can define outside, and you can call it uh, from another namespace. It doesn't need to be in the same namespace, and this is pure logic. Like, it doesn't matter where A and B comes from. It doesn't matter that it's HTTP request. It doesn't matter that it's if it's a query that you're making from the DB. It doesn't matter that if it's a value. It is something that you can live on your logic, and you can even unit test it using a downloaded values, for instance. Is how you would unit test this and see that it behaves as you want it to behave. And on the controller side, you get something that is easier to understand, and also you get the benefit of I want to evaluate this with core-async and get non-blocking I/O. This could we could have, instead of just A and B, we could have like maybe two or three other requests that could have been made concurrently, and Noly would handle this as well. It would make the request that could be made concurrently. It would make it concurrently, so you get benefits from concurrency. And if you want to run this differently, you just evolve it with a different engine. For instance, one thing that I think is valuable is when you are debugging the code, there's some problem that you can't understand. You can switch the engine from running async to running sync, because sync code is much easier to debug, much easier to understand than async code is. So you get the benefit of a simpler, uh, effectful code, and the separation, more separation, that you can move some parts of this to the logic. So I know this is a toy example, but this is just a way to visualize how it's possible to arrange the same function that we had in a way that is more decoupled. So having said that, uh, the question is like, why would you use Noly? And there are some reasons why, and those are not the only one. You can also find your own, but one of them is that async programming is hard, uh, especially core async. If you mess with core async, it's very hard to do it properly, and you run into a lot of pitfalls. So it's, if you have this done for you and you just uh, evolve the code, then it's much, you don't have to worry about it. And also, conditional code is present in everyday code. Uh, It's out there, and it's important for us to be able to express them in a way that is detached from the data they depend on. This is one thing that uh, Node provides, and also be able to separate those dependencies from how we execute them. So we can declare the dependencies and we can run them in many different ways with many different uh, strategies and interpretations without changing the definition itself. So uh, you get more maintainable code this way, because if you need to change something, change how it runs, it's don't need to change how you declare it. So in conclusion, just summing up, Nodally is meant to be very small. It doesn't tend to be a framework that solves a lot of problems. So we're trying to follow Unix principle, like write programs that do one thing and do it well, and work and programs to work together. So the idea is that this is the problem and that Node is solving, and it's not going to solve more problems than this. And I think if people could use Node to write complicated things, more complex frameworks, I think that's gonna be very nice. But Node itself is gonna be this that I just showed you. Of course, with probably more engines, probably support for closure scripts that we don't have at the moment, but it is possible. We have an engine that it is experimental running promesa, and I know that promesa runs in the JVM and it also runs in JavaScript, so it's possible that uh, we have also support for closure scripts. And now the current focus is we have some experimental engines that we don't think are mature yet for use. You can use if you want to experiment, of course, but we want to improve their maturity first. And the last thing is that, so this is how we are going to be using Nodely right now. So we're using it to run backend code, especially on queries. So the queries are HTTP or DB requests of things that you need to fetch from external, from outside, to run some particular task in your service. And we're not doing it for running uh, effect things that change the database, like write to the database or anything like that. And that doesn't mean that this is the only usage. That there are probably many ways that you can use this kind of tool, and we're happy to know if you have other things that you would like to use Noly on. And we also appreciate questions, issues, and contributions. Just don't be afraid to get in touch. We're interested in all the feedback we can get. So that's it. So thank you very much, and I'm open for questions now.